In our last video, we learned how to create coin-based transaction. You might have noticed that there is no transaction ID. There should be a unique transaction ID for every transaction. So in this video, we are going to create one. To create transaction ID, we need to convert all the variables in byte format and concatenate them together and then run the hash 256 function on it. So let's do that. So open up your blockchain module, blockchain, backend, core, and transaction. So let's delete this. Okay. So inside the transaction, so we need to convert all these variables and the objects into byte format first, and then we need to create a serialize function for this. So let's define our serialize function for the transaction object or for the transaction class. Define serialize self. So let's understand how this is going to work. So we have version, this is just a variable. So we can easily convert this numeric variable into byte format by doing integer to little endian, and it will be converted into byte. But this is the object itself, the transaction. So we need to create a separate serialize function for our transaction input, and same goes for transaction output. And lock variable is just a variable, and again we can simply convert it into the byte format. So create result variable. So this is where we are going to store everything. So result equals to, so we have self dot version, and we need to convert this into byte format. So let's do int to little endian. So in our previous videos, we have already defined these functions inside the util module, and version by default takes 4 bytes. And next is transaction inputs. So we need to see how many input objects are there in this list, and we can simply do that by using the length function. So do result plus equals to self dot tx ins and length. So this will give us the number of objects inside txins list. We can have more than one inputs in txins. For example, you want to send 100 bitcoins to George. You need to go through all the transactions that you have received in past from others. For example, we have received 10 bitcoins from Bob, 5 bitcoins from Joe, or 20 bitcoins from Alex, so on and so forth. Since we are sending 100 bitcoins to George, so now we need to combine all those transactions together in order to send 100 bitcoins to George. And now we have multiple inputs, and that's the reason we are checking that how many transaction inputs are there in this list. So the next step is we need to convert this length into byte format. So let's go ahead and do that. Go back to util module, define a new function called encode variant. So we are receiving the number of transactions as an input, and then we are simply returning as a byte. So if the transaction count is less than 253, so we would require 1 byte. If it is more than 254 and between 65,000, then it would require 2 bytes. And we are also adding some kind of prefix so that when we will decode these transactions, so we will know that how many bytes we need to read. And these are hexadecimal values. So we will be working a lot with hexadecimal values in Bitcoin. So let me quickly show you this. Go to Python interpreter, Python, and 65,536. So this is just the hexadecimal encoding of the numeric value. So let's go back to the transaction module and import this function that we just created, encode variant, and convert it into encode variant. Okay, so now we have converted the length into byte format. So the next is, since we have multiple objects of transaction inputs, we need to convert each and every object into serialized format. So let's create a for loop for tx in self dot tx ins and do result plus equals to tx underscore in dot serialize. So now we need to create a serialize function for the transaction input. So let's go to transaction input class and declare a new function called serialize. So to define serialize self, and first we need to convert the transaction hash and then the index. So let's go ahead and do that. So do result equals to self dot previous hash. So by default we know the transaction index is in byte format already, so we don't have to do anything, but we do need to convert the order. So we need to reverse the order. This is how the Bitcoin implementation is, and we are just following the same rules of Bitcoin. So let's go ahead and do that, reverse the order. And next is result plus equals to, so we have the index, and by default index takes 4 bytes, and let's convert it into little endian, into little endian self dot previous index, and it takes 4 bytes. This is a fixed number. And next we have is script signature. So script is the object itself. So that means we would require a separate serialize function for the script class. So let's go ahead and do that. So for now, we will simply do self.script signature. We'll come back to this. And let's convert result plus equals to int to little endian and convert self.sequence, and self.sequence as well takes 4 bytes, so we'll define that this is fixed. And finally we will return the result. We'll come back to this. We need to define a separate serialize function for the script object. We'll do that, and let's head back to the transaction object. And now what it will do is it will convert all the transaction inputs and it will add the concatenated value in the result variable. Let's save it, and let's go ahead and do the same thing for the transaction output as well. So even for transaction outputs, we know that you can transfer money to multiple people in the same transaction. For example, I can send money to Joe, Bob, Christy, Arena in the same transaction if I have enough money, right? So transaction output can have multiple transactions as well. So we need to define the same length function that we defined for the transaction input. So let's go ahead and define that. Result plus equals to, and same function we can use encode variant, and length, since it is a list, so we can do transaction outs, and it will convert the length into byte format. And next we need to convert all those transaction outputs into the serialized format as well. So do tx underscore out in self.tx outs and result plus equals to tx out dot serialize. So now we need to create a serialize function for transaction output as well. And before we do that, let's take care of the log time equals to int to little endian and self.log time, and it also takes 4 bytes, so this is fixed. remove this extra equal to, save it, and finally we will do return the result. Return result. So now let's go to the transaction output and take care of the serialized function. So define serialize, self amount. It's simple. So since this is a numeric, we can do int to little endian like others. And amount is fixed. It takes 8 bytes. So let's do amount and 8 bytes. So it will convert it into byte format. So next is result plus equals to self dot script public key dot serialize. And finally, we will do return result. So here as well, we have the script object. So we need to define a separate function which is pending in the transaction input as well. So now we will take care of the script serialize function. So let's save it. Let's go to the script module. And in script module, we only have the stack based operations. So that means only push and pop operations are applicable in script. And the functionality of loops is limited in script. And that is because of few obvious reasons. Because it is possible that if some bad actors push something in script, and because of that, it can go into infinite loop. And this would be an easy way to attack the network. And this attack is called denial of service, or DOS in short. So in script programming, we have two kind of things. So first is the opcodes, and second one is the element. So these numbers, the constant values that we discussed earlier, these are the opcodes. So in script, we have opcodes like hash 256, check signatures, etc. We will see all these opcodes when we will implement the functionality of transaction signatures. And for now, we don't have to deep dive into these opcodes. And let's see and implement the serialized function in script. Okay, so let's go through it and understand what exactly we did. So first import these int to little endian. So to from blockchain dot backend dot util import int to little endian, save it. Okay, now those errors are gone, and we have the encode variant as well. So let's import this one as well, code variant. Let's try to understand the serialized function here, what exactly we are doing. We find the result variable, and we have assigned the empty byte here, and then we are looping through the commands, and we know that we have these commands here, and in the script we also assigned the commands here. So these are the operations. So this each constant value is assigned to a or tagged to a very specific operation, for example hash 256 or check operations like that. And this is the element, and this is the actual data element, and h160 is the public key where we have locked our bitcoins, and only the rightful owner of the bitcoin can spend or unlock these transactions. So what we are checking here is if command is equal to int, we know that is a opcode, and all opcodes are below 256, and it would require 1 byte to store, and we are converting it into int to little endian. So this is easy one. But if we have something like this, wherein this is the data element, so it will automatically come in the else loop, and then we are checking the length of the command, and if length is below 75, so we are converting that into byte format. And if length is greater than 75 and less than this number, then what we are doing is, so in Bitcoin there are predefined kind of operations already defined. So this signifies that if length is greater than 75, then automatically add the 76 code there, so that when we'll decode the transactions, it will be easy that how many bytes we need to read from the data. And if the length is greater than from this number and less than this, then we are adding a second push data code. So this is a signal that we have 2 bytes to read when we are reading the transaction. So here we are allocating the 2 bytes here. And then finally, we are adding the data element itself in the result. And finally, here we are doing the total length check of the result variable, assigning it to total. And then we are doing the encode variant of total. So it will assign the total bytes of the result that we have plus the result itself. All right. So now we have encoded the script as well. So go back to the transaction, and we have defined this serialization method inside the transaction input class and the transaction output class. So let's check it there. Right here. Okay, let's fix this. We should have equal to here. So we are doing self.script signature and call serialize here. And we have already called the serialize function here. We have serialized the complete transaction object, and now we can create the hash. And let's go ahead and import the hash 256 from util. Hash 256. Go back to the transaction class, create a new function, hash self. So this will return hash 256, the serialized object that we created. So this will return the data in byte format, and we need to reverse the order of the data. This is how it is in the Bitcoin official version, and we are just following the same. So let's reverse the order and also add the documentation here. So binary hash of serialization. And now create one more function, ID function. So this function will create the transaction ID, self documentation, human readable Tx ID, return. So this will call the hash function that we created, hash, and it will return the data in binary format or in byte format. We need to convert it into hex. So let's do this. And now we have the ID function ready. So we need to modify the Coinbase transaction a little bit. Remove this from here and add one more line, Coinbase Tx, and let's call the ID function. So do Coinbase Tx dot transaction ID equals to Coinbase Tx and call ID. And now we have assigned the new variable transaction ID in the Coinbase object. And now let's return this object. Save, go back to blockchain module. Now we can replace this with transaction ID. So do Coinbase Tx dot Tx ID that we assigned and save it. Clear our blockchain file. And let's call this now. Add the breakpoint. And now we should have the transaction ID created. Awesome, it worked. We have the Merkle root, so that means the transaction ID is being created correctly.